Hi everybody, this is your Chapter 13 screencast. It's your test review. I hope you like it. I tried to make it short, brief, and focused. So here we are, changes in state, the common states of matter. Notice we have phases of water. So the solid phase of water is ice. The liquid phase of water is water, and the gas phase of water is water vapor. Next I want to focus on these states of matter and these changes. A solid can directly change into a vapor, but it's very uncommon. It happens with dry ice, and next week we're going to do a dry ice lab. Notice I've drawn the vapor pressure of the solid, and it's a lot more than atmospheric pressure. And so that's why dry ice sublimates. It goes from solid to vapor directly. Now a solid usually melts and becomes a liquid. And a liquid usually evaporates if you add energy and becomes a vapor. If you extract heat, a vapor changes to condensate. And if you extract more heat, the liquid will freeze back into a solid. I just want to point out normal pressure. What is normal pressure? It is 1 atmosphere at sea level, 101.3 kPa. So that means the normal melting point at 1 atmosphere is 0 degrees Celsius of water. That's the normal freezing point also. The normal boiling point of water at one standard atmosphere of pressure is 100 degrees Celsius. Oops, sorry. Don't know how to advance the slides here. Okay. Next, I have a comparison for you on evaporation and boiling. So over here, I have a diagram of evaporation. The liquid molecules on the surface have enough kinetic energy to be able to vaporize. This is a surface phenomena. The liquid is not boiling. Once the particles with the greater average kinetic energy leave the surface, the liquid is actually cooled. That's why when you sweat and the liquid evaporates, you are cooled. Again, the particles with the highest kinetic energy are the ones that leaving behind the ones that have lower kinetic energy. How can you speed up evaporation? Well, you can raise the temperature of the liquid, or you can slow down the rate of evaporation by cooling the liquid. Let's go over here and take a look at a comparison of evaporation and boiling. I want to point out that evaporation, the vapor pressure, is less than atmospheric pressure. When does the substance begin to boil? When do bubbles form and rise from the bottom of the liquid? When the vapor pressure is equal to atmospheric pressure. Again, evaporation is on the surface. The liquid is not boiling. The boiling point, when you are at the boiling point, when you're boiling, the vapor pressure is equal to atmospheric pressure. Evaporation, you're vaporizing below the boiling point. Here is a comparison of a solid, liquid, and gas according to kinetic theory. I want to make sure you're familiar with these terms. So solids, we can say the particles are moving. The particles are always moving in a solid, liquid, and gas. But here's a comparison. In a solid, the particles are vibrating in place. The particles are close, and so that's why we say a solid is dense. Solids are difficult to compress. Examples of solids would be metals, crystals, and salts. Let's move over to liquids. You know liquids flow. And there are intermolecular attractions which keep the particles close. That's why liquids are incompressible. You cannot squeeze 100 milliliters into a 90 milliliter container. Let's go to gases. There are quite a few things that you should notice. Gases flow. The particles are very energetic. They are colliding elastically, meaning they never lose energy. They never slow down. They're not attracted to each other at all. Gases are compressible. There's a large amount of space between gas particles. You can put gases in a small volume or a bigger volume. Again, that's because of the space between the particles. The particles are constantly moving, and they are moving independently. That you could characterize the gas particles as small hard spheres with insignificant volume. I have a few things I want to mention to you about gases and atmospheric pressure. Again, what causes gas pressure? Well, it's the simultaneous collision of particles with the container, or inside a balloon, or on the Earth's surface. We are experiencing gas pressure, actually atmospheric pressure. Now, vapor pressure is the pressure that the gas exerts above a liquid. Over here, I drew a container with a lid. The liquid, once I put liquid in the container and I put the lid on, some of the particles will vaporize, the surface particles, right? And they will build up, vapor will be built up in the space above the liquid. And again, these particles are more energetic. They are colliding with each other and with the walls of the container, and so they are creating vapor pressure. So the vapor pressure builds up until we reach dynamic equilibrium, and that's when the rate of evaporation is equal and opposite to the rate of condensation. Again, a warm room, this will happen quickly. A cold room, this will happen more slowly. I'd like to look at temperatures and pressures, and I'd like to look at the comparison between the Fahrenheit, Celsius, and Kelvin scale. So, let's see. You may remember that average kinetic energy is directly proportional to the Kelvin scale. Why is that? Because Kelvin scale, the particles are always moving until you reach absolute zero Kelvin. And so the Kelvin scale talks about average kinetic energy of the particles in a solid, liquid, and gas. And so it doesn't make sense to have negative numbers. On the Celsius scale, you have negative numbers. The normal melting point, of water is 0 degrees, and the normal boiling point is 100 degrees Celsius. I thought it would be fun to show you this graphic because sometimes students ask me to say things in Dutch, and this happens to be Dutch, and it says kokend water and smeltend ijs. This letter is a combination of an I and a J. It's called a lange I, or a long Y, if you will. Smeltend ijs, it's when it's actually melting ice. And kokend water is actually boiling water. Let's go over here to this box of gas. Notice the gas particles are colliding. They're moving in all different directions. They're far apart, and standard temperature and pressure of 1 mole of gas is defined as 0 degrees Celsius and 101.3 kPa. Those are standard temperature and pressure conditions of a gas. Let's move over here to this diagram. You see, at the top of the mountain, you're experiencing lower air pressure. Below sea level, or down here, you're experiencing more air pressure. At sea level is the standard. You can actually boil water at a higher elevation at a lower temperature because of the lower pressure on the surface of the liquid. Below sea level, you boil above 100 degrees. Again, standard pressure is 1 atmosphere of pressure at sea level, or 101.3 kPa. I added this slide on a comparison of solids. You may remember I had all these models in the classroom, and I just want to remind you again that there are ionic solids or crystals. This is a classic salt model, and you know salt has a very high melting point, 800 degrees Celsius. Why is that? Because of the strong ionic attraction between the anions and the cations. Let's look over here at molecular solids. A molecular solid is held together by an intermolecular force. Examples are dry ice, regular solid H2O, and sugar. If you look at a few things here, again, this is water. This is a model of ice. Notice that the box opens up as these hydrogen bonds stiffen up. The melting point of ice is very low. It's 0 degrees Celsius as compared to 800 degrees Celsius for an ionic solid. The melting point for sugar, which can be melted on the stove, is 135 degrees Celsius. You cannot melt salt on top of the stove. I hope you enjoyed this 11.5-minute video. I hope you'll watch it. I hope you'll review and let me know how you do. Bye-bye.